Hello everyone, we're making a handle to operate the quill on my Alexander Master Toolmaker milling machine. Now I've selected a lump of steel to use as the hub of this handle, but in the last video we discovered that it was too short and it needed to be extended so I can actually machine it in the lathe. Now we attached a piece of aluminium to the back of that steel hub and we've turned the extension piece down to around about the same diameter as the hub itself. It's now time to do a little bit more work on that hub. I've now brought the hub over to the Alexander milling machine and mounted it in the chuck of this indexing head. Now the indexing head I've set up. I'm not going to run through the setting up procedure in this video as I've already covered that in another video, and it actually shows how to set this head up on the table of the milling machine and also a dividing head as well. So if you want to see that video, you'll find a link to that in the notes at the end of this video. We're looking at the side of the milling machine here. We have the vertical head at the front and we have this hand wheel at the back. Now this hand wheel, if I turn it anti-clockwise, this will move the machine in the y-axis, and you can see that the vertical head is going forwards. So when I turn this handle anti-clockwise, the vertical head goes forward. If I stop, turn it the other way, you'll see that this is now going clockwise and the head is coming back. So if I want to go forwards, I go anti-clockwise. If I want to come back, I go clockwise. Now if I want to move the head from one particular position to another position, then I need to know exactly how far that head has moved. And we gauge that by the scale wheel that's on the handle. Now let me bring you in closer and then I can explain what's happening here. Here we are close to the y-axis scale wheel. The handle is here, you've got the scale wheel here, and you can see that there are a whole load of divisions. Now the divisions on this scale represent the amount of travel that the head has made. So if we move just one division from there to there, the head has moved 1/1000th of an inch in that direction. If I move it 3 more, 1, 2, 3, that's another 3 thou in that direction. You'll notice that this wheel has got a 0 point, which is just there. And if we count the number of divisions, that's 5, 10, 15, and now it comes up to 20, 40, 60, 80, 100, 120, and then it goes back to 0 again. Now what that means is one rotation of this wheel, the head will move 125 thou. So if this wheel was going anti-clockwise, the head would go 125 thou in that direction in one full rotation of the wheel. So the scale wheel at the moment is attached to the handle. If you move the handle one way, it follows the handle. If you move it the other, it follows the handle. Now the wheel at the top isn't really a wheel, that's the reed line. So when we're taking measurements from the scale wheel, we take them off of that line. So that gives us a datum to look at. What does it mean when the 0 of the scale wheel now comes in line with the reed line? Is that a certain position of the head on the machine? No, it isn't. This reed line, if I undo this ring here, which is the lock, the scale wheel is now not connected to the handle anymore. So it doesn't represent anything at the moment. And the way that we use this is we would position the head in a position where we know exactly where it is, and then we'd take measurements from that point. So we would put the head in a position, say now we know that it's at a datum, so we would bring the scale wheel around so the 0 is against the reed line just here. And then we would do the lock up, which I'm turning just here. We would do this lock up like that, and now the scale wheel is locked onto the handle and it would stay with the handle again. Now something else we have to be aware of is a thing called backlash. Now all backlash is all the slack that's in a system. Now this handle here is on a shaft and it goes through a little gearbox on the inside of the milling machine here. That little gearbox drives a shaft that runs in this direction, and that threaded shaft goes through a nut which is connected to the head. So every time you turn the wheel, that turns that shaft and it pulls or pushes the head through the nut. Now because all that system has got a certain amount of slack, it can make things misread on the scale wheel. Now, if I move this clockwise, so the handle's moving clockwise, I bring the 0 to the read line, which is just there. I will now put the lock on. Just need to find it. There it is. So I've now locked the head. The head can't move. Now we just moved the wheel clockwise to bring the line up to here. Now, if there was no slack in the system, then I wouldn't be able to move the handle because the head is now locked. But if I move it now anti-clockwise, which is the opposite way to where we came, it now goes back 5, 10, 11, 12, 13, 14 thou. So we've got 14 thou of slack in the system. And that's what the backlash is. Now all machines are going to have a certain amount of backlash. Possibly some of the brand new CNC machines with the anti-backlashing systems in them, that may be different, but it's always best to assume that you're going to have backlash, then you're not going to be disappointed later on. So this milling machine has got backlash, my lathe has got backlash, my bench drill has got backlash. Now, how do we get on taking the backlash into account? Now, the first thing we need to do is establish a datum on the job. Now, how we get to that datum I'll be showing a little later, but let's assume that we now know that the head is directly over a known point, and we've got to that point by moving the handle in an anti-clockwise direction. So at that point there, we know that the centre of rotation is over the edge of our job. There's just an arbitrary number on the scale wheel, so we will loosen it. We will then bring the 0 around here. Now we got to that point by moving the wheel anti-clockwise. So if we moved it clockwise from here, we see the backlash there. But as soon as we get to the end of that backlash, that's the datum. So we could go back, come back in this direction, and as soon as that 0 gets to the read line, which is there, we know that we're at our datum point and the centre of rotation is over the head. So as long as we go in an anti-clockwise direction, we can measure from that point. So if we turn it round 1 whole turn, we've just gone past it, we go 2 whole turns, we know that that's 2/8 of an inch, which is 1/4 of an inch from our datum. So we've now moved our handle 2 revolutions anti-clockwise, and we've taken the head in this direction 250 thou. But really we only wanted to go 125, so we need to bring it back 1/8 of an inch. Now if we turn it clockwise, we're going to bump into the backlash. There's the backlash there, and we go back. If we now take it back the full turn, which is when the 0 comes round there, that's 125 thou minus the 14 thou of backlash. So it's inaccurate. But there's no problem. All we need to do is go back another turn. Now that's taken it back to the approximate position of our datum, less the backlash. There's still no problem, because what we do is go another turn, so we're now past our datum, but we need to remember how far past the datum in turns. So we are 1 turn past the datum, just there. So it's 1 turn past the datum plus the backlash. If we now go clockwise again, the first thing that happens is we go into the backlash. There's a backlash, there's the 14 thou, that now is taken up there. And now as we go forward, when the 0 point comes to the read line, which is just there, we bang over our datum again. The backlash has been taken up, and now we can do another measurement. So from there we can now go 1/8 of an inch, 125 thou, by moving this handle 1 whole turn, which is coming up to 120. When the 0 gets to there, we are now 1/8 of an inch, 125 thou in that direction from our datum line, just like that. So if we want to move the head more than 1/8 of an inch, we have to move the handle more than a whole revolution. Now, the interesting thing here is you've got to remember whereabouts you are. So you've got to start counting turns so you don't get lost. Say we want to move the vertical head in this direction, and we want to move it, say, 510 thou. Right, 500 thou is 1/2 an inch, which is 4/8. So we need 4 turns of the handle plus 10 thou. So we want to go in this direction, so we need to move the handle anti-clockwise. So we move it 1 turn, that's 1/8 of an inch. 2 turns, that's 1/4. 3 turns is 3/8. The fourth turn here is coming up to 1/2 inch when that red 0 gets to the line there, and now we want to carry on another 10 thou. Each of these divisions are 1 thou, 1, 2, 3, 4, so that's 5 thou, and that is 10 thou. So we've now moved the head 510 thou in that direction from its starting point. Let's just have a look at my last sketch. Now you notice here this is the locking plate which will lock onto the shaft of the quill, and at the bottom there is a screw. Now this blue screw retains the bottom part of that green plate. Now you can see that it comes through the hub on this angled surface. Now I need to get the hole drilled and counterbored before I do the angled surface, so that's why I've put the hub in the indexing head on the mill. I want to drill and counterbore that hole. We're also going to need a thread in there as well. The hole I want to drill I've roughly marked out just here on the top of the job. In fact, you may be able to see a little centre dot there. That's really there as a sanity check, so when I work out the position using the machine, that will just confirm that we are in the right position. Now, to get the machine to do the measuring, I'm going to need to know the edge of the job around here. Now the way I'm going to find that out is with this little device, and it's called a wobbler. Now you notice that the wobbler has a boss at the bottom. Now that boss is exactly 5mm in diameter. Now the way you use a wobbler, you will bring it down here, start the machine so it's now rotating, and then bring the head in this direction. As the wobbler touches the job, when it becomes parallel with the periphery of the job, it will kick sideways. At that point, we stop turning the y-axis handle and we turn the motor off. We know the outside face of the boss is parallel to the outside face of the job. As the boss is 5mm in diameter, we also know the centre of the boss, and therefore the centre of rotation of the vertical head, are both 2.5mm away from the side of the job. Now, if I start moving the head again in the same direction and using the scale on the Y wheel to measure the distance, I can move the head exactly 2.5mm. This will place the centre line of the vertical head directly over the edge of the job. If I then measure the job and then cut that dimension in half, I've got the radius of the job. If I move the head in this direction, that radius, that should get me bang over the centre line of our hole here. Now we do need to work out the position in this direction, but we'll be doing that a little later. Now we know how to move the machine in its y-axis, let's look at the job and turn the motor on. The boss of the wobbler is away from the side of the job, so it's wobbling. I'm now turning the y-axis handle slowly anti-clockwise. The vertical head is moving closer to the job. Now watch the boss. As it starts to rub on the side of the job, its wobble will reduce, and then ping! As soon as the wobbler kicks like that, I stop moving the y-axis handle at once and then turn the motor off. I've turned off the rotary converter so you'll be able to hear me. Now the wobbler has kicked over, we know that the centre of rotation of the vertical head is 2.5mm from the edge of our job. Now before I start moving the vertical head over, what I want to do is take out the wobbler and replace it with a long centre. We now bring the table up. So the centre of our centre is pointing directly down, and the line is 2.5mm from this surface. We know the centre of rotation of the vertical head is 2.5mm away from the side of the job in the y-axis. Before we can line up the centre with the side of the job, we need to zero the y-axis scale wheel. Be careful as you do this, you must only rotate the scale wheel and not the y-axis handle. 2.5mm is 98.4 thou. So we're going to move the head of the milling machine in this direction 98 thousandths of an inch. So I'm going to turn this handle anti-clockwise. 80, 90, 5, 6, 7, 98th thou just there. Now we've moved the head 98th thou, its centre of rotation is directly over the side of our job. This position will be our datum point, so we need to zero the y-axis scale wheel once again. Just like that. The next thing I need to do is measure the diameter of our job. Now this was a 2-inch bar of steel, so I have a 1 to 2 inch micrometer here. Just there, and that is showing 996. So the diameter of our job is 1.996 inches. If we divide that by 2, it's 0.998. So that's how far we've got to move our vertical head over to get to the centre of the job. 998 thou. Now the radius of our job worked out to be 0.998, 998 thou. So that's 7 turns of the handle, which will give us 875. So we need to go anti-clockwise 7 turns. 1, 2, 3, 4, 5, 6, and 7 turns is just there. 7 turns plus 1.123, so 123. So we go 20, 40, 50, 123. 1, 2, 3. Just there. Right, now let's just raise the table again and see if we're near the line. And we are spot on. Now that's good. That's worked out well. Next thing we need to do is work out the whereabouts on the x-axis we have to be for that hole to be in the correct position. Unfortunately, we're going to have to stop just there, but working out the hole position in the x-axis is going to be the first thing we look at in the next video. If you like this video, can you please give it a big thumbs up? It'll only take you a couple of seconds and it's really good for the channel. And with that, this video is at an end. Take care everybody. I'll see you next time. Could you do something like this? Of course you can.